Hey, good morning. Let's get started with our lecture. Miraculously, I find the pen underneath the door. Otherwise, we're done today. Okay, last lecture we talked about the system causality. So this lecture we're going to continue on the system classification or properties. And if you recall that we have three different properties. Okay? So system causality. So essentially, is a system causal system or is it a non-causal system? Okay, so this one is done. So now let's look at the next category, which is system linearity. So that's the second category. And once we finish this, we have one more. It will look at the system time variance or time invariance. Okay. So before we talk about the system linearity, I want to introduce a simple math concept for our purpose of lecturing. So the first I want to introduce a concept is called operators. Okay, so operator first of all, operator is a math concept. So what do we use it for? Okay. For now, I want you to think of a system. Basically, we're going to think of a system as an operator. And we can use literally any symbol to represent this operator. You can use M, right? This is basically, it's just a symbol. You can use any symbol to represent this operator. So here's an example how you can actually use an operator to represent a system. So let's see, for example, okay, given such system. Okay, so let's say you have a box here, you have an input to the system, and then you have an output. Now, let's specify the system out. So basically, the current system here is a derivative operator. So the system is very simple. Whatever the input is given to the system, and then it spits out its derivative. Right? So the output here is derivative of the input. Right? Or sometimes you just write it df right over dt. So that's a system. Right? Now, if I choose to use an operator to represent the system, okay, instead of very specifically to use a derivative operator, so you could also just say, okay, here is a system. I use M to represent this operator. And then input over here, and then output, right, is y of t. So the output here, what you could do is you just see m f of t. So now you have a very general expression, right, to represent the system. So you're using this simple m as an operator representing whatever the system could be. Right? This is a simple one. It could be more complicated than this. Just a sec. Let me turn on my little highlighter. Good. So that's the idea of operator. Right? You're using a simple symbol to represent maybe a much more complicated operations on the input, right, based on the system. Good? Good. So if you understand this, then I'll give you a few more examples, but for now, you probably don't know them yet. But during this term, you're actually going to learn quite a few different operators. Okay? So I'll just see what you're going to learn. So for example, you're going to learn very very soon you're going to learn this operator called convolution. And we use a star. Okay, we use a star to represent this operator. Okay, so basically, we'll see what convolute what. Okay, that's an operator. And you're going to also learn another type of operator called Laplace transform. Okay, so we use this like L, like a music symbol, but it's L. Okay, Laplace, and then brackets. Okay, whatever you put in the bracket is a system input, and then you spit out the corresponding transformed signal, which is so-called Laplace transform. Okay. At the end of this course, we're going to learn another one called the Fourier transform. And so Fourier transform using letter F at here to operate on the input signal, give a transform signal called a Fourier transform. That's another operator. So a very specific operator, very much like a derivative, but it's a more complicated operation. Okay. In 248, you're going to learn an operator called a gradient operator. So using this inverted triangle here, that's called a gradient operator. Okay. In Greek pronunciation, this is called the nebula. Okay. The same thing in 248, you are going to learn another one called divergent operator. So it's an inverted triangle followed by a solid dot, basically a dot product. Okay. So that's another operator. And one more to give you here called the curl operator. So this inverted triangle here called del. So del cross. So this is a cross product. Okay. So all of this will be examples of operators from this class and then the other class, of course. And of course, you could have many other. This is our very specific. Definitely can have many, many other examples, right? So in summary, okay, so when you have a system and you give an input, okay, so sometimes I use F, some use the X. It's just bear with me. That's fine. And then you have an output. Okay. That's a general description of a system. Then equivalently, I can now use my operator, okay, M, to illustrate or to demonstrate the current system. Okay. So if you see inside a box, it doesn't necessarily have to be M. It could be other symbols. But as long as you see something like this, okay, this essentially is the operator we're talking about here. Okay, good. So let's make sure we're all on the same picture and what operators are. If you ever see this thing here, then you'll know what this means. Okay. Again, I want to emphasize is that whenever you see a symbol bracket, okay, it doesn't really mean, okay, this symbol multiplied by whatever inside the bracket. Okay, so it's going to be crystal clear. Okay. It always means it's an operation. Right? It's like a simple function. Basically, operator is like a function concept. So now let's go to exactly what we're going to cover today, linearity. How do we categorize a system, whether it's linear or nonlinear? So here is first the theorem or definition. I'm going to present it to you. Okay, so this is the whole picture right here. Then we'll get into detail how we can make use of this. Okay, a linear system. A linear system is a system that obeys the following property. It has to obey two properties. One property is called homogeneity. The first one, we're going to show what it is. And the second one is called additivity. So we're going to use this general big picture to show whether a system is linear or not. But we're going to have to show what this means and what this additivity means. Okay, good. So let's go step by step. So first, actually I'm going to look at the additivity first. All right. So first, I'm going to assume I have two different inputs. Okay, so I'm going to let x1 of t and x2 of t. So let these two, let them be two different inputs. Right. So what this means is, so first of all, I'm still using a single input, single output system, okay, to demonstrate all of the concept here. So you can see if I have a system input which is using symbol x of t, so then over here, what I mean is you replace x with x1 of t, so that's one kind of input, or you replace x with x2 of t, which is another kind of input. Okay, so that's basically what I mean by two different inputs. It doesn't mean I'm applying both of the inputs at the same time to the system, and then I become a multi-input system, right? Okay, so we're just saying you could give different inputs to the system. So now let's look at the first property, so-called additivity property. Okay, so before I give you the meaning additivity property here, so again, based on the inputs, we could actually write down some information first. So given inputs x1 of t, given this input, right, given this input to the system, then obviously you will generate an output. So let's call an output generated by x1 of t, let's call it y1 of t. Similarly, you give x2 of t, and they will generate a different output, let's call it y2 of t. So one way or another, it's not up to you, right? As long as the system given, you have this input, you have the output. You have this up, you have another input, you have a different output. Good? So this essentially is like you have a cause number one, then you have an effect number one, right? If you have a cause number two, then you have an effect number two. So different cause, different effect. Good. So, but we introduced the operator as concept. So how can I describe the first situation or the second situation using the operator symbol? Right. So basically, if my output is y1 of t, and that is because of the input is x1 of t. So basically, you have your operator m, which is a function basically. Okay? You have your operator m operating on the input x1 and produce outputs y1. Okay? That's why I have given you a heads up. It's a little bit abstract here, right? If you look at, if I don't see anything, I just write down this one here. It could be anything, right? But now we're giving it a certain specific meaning. Okay? Input and output concept, a system concept. Okay? Similarly, for the second one here, you can have y2 of t equal to m x2 of t. So those are, you know, it doesn't matter what we do, right? And this is essentially what's really happening to the system. Okay. So now let's look at the so-called additive property. Okay. So I'm going to give you a third scenario now. I'm going to let the third input, I'm going to create a third input. The third input is x1 of t plus x2 of t. So we created a different input. Right? This is a new input. But this new input is an addition of this original x1 and x2 inputs. Then, given this new inputs, right, what will be the new output? Okay? So of course, you can immediately write down using the symbol, right, using the operator symbol as we have used, that equal to m bracket x3 of t. Of course, we have defined x3 of t, so this is x1 of t plus x2 of t. So your new output is based on the new input, which is x1 of t plus x2 of t. So far, so good, right? Good. So the key is the next line here, right? We need to check, okay, we need to check if this y3 of t, okay, which is m x1 of t plus x2 of t, okay, so this new output, is it equal, first for now I'm putting a question mark, is it equal to this m x1 of t plus m x2 of t? Okay, so I was babbling for a little bit long time. So really, what we're interested is this key expression here. Okay. So let me reiterate this expression a little bit and see what exactly are we looking for, right? First of all, you should have a clear meaning of what the left side is already, right? The left side basically is your new output of y3 of t equal to, of course, is operator operating on the new inputs, which is x1 plus x2. I want to see if it's equal to the addition of these two. And these two on the right side, the first one here, what's the first one? That's if you see it using Lee language, right, not using the operator. The first one here is the system output due to the input x1 of t. And the second one here is the system output due to the input x2 of t. Okay? So the idea is the system's output, when the input is addition of the original two inputs, actually produce the same output as the system addition of the original two outputs? Okay. I'm wondering if that's a clear description of what this means, right? So if this is a yes, right? Okay, then this is what we call additive property is proved. If no, then additive property is not true for this system. So that's basically what additive property, right? You look at this expression, so essentially it boils down to the expression here. Can you prove the left side to be the same as the right side? The left side is system output when input is combination of the original two inputs. Right side, the system outputs when you add the two outputs, right? When it separately, when the input is x1 and x2. Okay? So all we're gonna do, okay, the next example I'm gonna show you is to demonstrate how can we apply this property, or how can we check to show that the system satisfies the property or not, additive property. Okay. So let's take maybe a few seconds to let it sink in. Let's basically you look at the expression. I want you to ask yourself, questions are, what's this symbol? What's this symbol? Right? What does the bracket mean? And what does the equal sign mean? Right? What does not equal sign mean? So those are simple questions you can immediately ask yourself. Okay. If there are any questions, right? Raise your hand for now, but or you jot it down, and we can come back to it. Okay. Yeah. Good. So let's look at examples here. Okay. Yeah. Now maybe before I give you very specific examples, let me demonstrate how you can actually use this property. Okay, so let's give you an example first. Okay. Now suppose that you have a linear system. So this is kind of I'm not asking to prove whether the system is linear or not yet, right? So basically, you know already. Okay, so I told you this is a linear system, right? And the linear system, okay, with input, okay, t to the power of k, and its output is cosine kt. Okay, so that's a very strange system, of course, but anything can happen, right? So essentially, to demonstrate it, here's the system t of k input, and then here's the output cosine kt. What could be the k? K could be 0, could be 1, could be 2, could be anything. Okay, it's an integer number. Then here's the following now. So suppose that, let's say, I have the first input, which is t to the power 2. That's when k equal to 2. And the second input is t to the power of 4. And third input is t to the power 6. You can create many inputs as you can. Then obviously, according to the description of the system, when input is t to the power 2 or t squared, your output, let's call it y1. What would be the output if the system input is t squared? Cosine 2t. Good. The second one, cosine 4t. Third one, cosine 6t. Okay, that's fairly straightforward, right? Okay. So now let me ask you this question. See if you catch. Now you can catch the additive property now. If the fourth input is an addition of x1, x2, and x3 of t. If the fourth input is addition of the 3, then what is the corresponding output? So we don't even know what the system equations are, right? We don't even have it. But all we know is the system is a linear system. And now I have a new input added here. What do you think the new output would be? Sorry, come again? What's your name? The one on the first row. Yes. No, you're here. Yeah. No, you're just you. Yes, you. Yeah, what's your name? I'm talking to you, sorry. Yeah, what's your name? Josh. Yeah. So what do you think the answer should be? Maybe a quick addition of all the outputs. The addition of all the outputs. Right. So addition of the outputs here, meaning here, here, here. Okay? And that's basically, if I had to write it, this is, this is m x1 of t, right? This is m x2 of t. This is m x3 of t. Good? Yeah. So, of course, Now you get cosine 2t plus cosine 4t and plus cosine 6t. So that's the application. This is what I call application of the additive property, because I have knowledge that this system is a linear system. Right? So you're applying okay, good. So that's actually a simple system, right? A simple concept of how to apply the additive property. But I'm going to show you how we can prove the additive property, okay? Whether the system is satisfied additive or not, all right? Yeah. So maybe what's better is let me finish the homogeneity property first, and then we'll look at both as a whole to cover an example. Okay. So let's look at the next one here. So this is additive property number 1. So let's look at the second property here. Homogeneity property. Okay, let's look at the definition. What homogeneity property is? We'll follow very similar to the descriptions as in the property number 1. If x of t is an input, okay, so x of t is input, c is a constant. So we're giving a constant value c, then c times x of t, right? So now we're creating a new input. We call it c times x of t. So this is another input. If x of t produces one output, then c times x of t will produce another output. Right? So the following definition of homogeneity would be basically if your input is if your input is c times x of t, then m of cx of t means what is the output, right? Based on this input. Okay? And then if this equal to c times mx of t. So before we move ahead here, so essentially I just want to reiterate here. So the first term here, you get this is the output corresponding to cx of t. And this is the input. Okay, so that's first term, the left side. And this side here, of course, this is very straightforward. This is the output, right? When input is x of t. So you look at this equality expression here. What this means is when your input is x of t, if your output is changed to cx of t, then the corresponding output is related to actually the original output by just multiplied by the constant c. So that's what this expression is telling you. Right? If this equal is satisfied, then the homogeneity property is satisfied. So we also call it homogeneous property. We call it homogeneous property is satisfied. Now some students pronounce this homogeneous. Actually, if you look at Webster dictionary, homogeneous, homogeneous, they're actually two different words. But they have a very, very similar meaning though. Okay? Yeah. there you go. That's homogeneity. Okay? Yeah. So now, if you go back to the original statement of a system linearity, we said that the system is a linear system only if the system satisfies both of the property at here. If a system only satisfies one of the property but not the other, then the system is actually not a linear system. Okay? Yeah. So you have to basically make sure the system satisfies both systems in order before you make a conclusion that the system is linear. Yeah. Good? Okay, so now we're ready to look at examples, but I'm also ready to present you a shortened version, of the property, which combining both of the additive and homogeneous property together. All right? So this is basically called superposition property. Superposition property. So the idea basically is a system is linear if the superposition property is satisfied. It looks much simpler, right? Instead of checking two properties, now you just had to check one property. Here is the writing of a superposition property. System is represented by operator M. Input of the system is C1 x1 of t plus C2 x2 of t. Okay, so this is your left side. Here is the input. What does it equal to? It's equal to C1 m x1 of t plus C2 m x2 of t. Okay. Messy here. Okay. That is superposition property. So you look at the superposition, but I want to ask exactly the same question here, okay? So you look at this expression on the left side. What do we call the whole expression inside the bracket? This whole chunk right here, what do we call it? Input, exactly. Right? This looks a little bit scary, but it doesn't matter. Anything inside the bracket is called the input. Right? So this is basically your input. And you look at the input here, what do you observe? The input is basically, it's a combination of x1 and x2, right? But it's not just a simple addition. There's also scaled version of x1 plus the scaled version of the x2. If you compare this to the additive property doesn't have C1, C2 here. Right. So maybe I should also iterate the C1 and C2. They are constants. Okay, so they're not variables. Okay. So the left side, the input is this, produce an output. Then the corresponding output would be the same as, according to the superposition property, right, would be the same as C1 times the system output when the input is x1 plus C2 times the system output when the input is x2. As long as this is satisfied, okay, this is the superposition property. And you check this is satisfied, then a system basically is linear. Any question on this superposition property? Right? You can actually clearly tell it's a combination of both additive and the homogeneous property. Okay. Good. Okay, enough of the writing here. So let's look at examples to fully understand how we can show a system linear or nonlinear. So I'm going to use a real life example right here. Okay. We all love Starbucks coffee. And here's your observation. you go, you spend some money, and then you see how much you get for coffee. So let's say you spend $2 and you get one drink. Okay. Actually, it's more expensive than that now, right? And you spend $4 and you saw, oh, I got 2 drinks. Okay. And you spend $6, you get 3. You bet $8, you get 4. Okay. So that's so on and so forth. Okay. So that's Starbucks, sometime in the old days. So then you let, and so now you say, okay, is this a linear system or not? Okay. So it's a little bit nerdy, but any system, anything can be described as a system, right? So you want it to see if it's a linear system or not, and you want to prove it. Okay? So here's what you would do. You try to model it first, and then you want to show the linearity using the 2 properties. Okay? So I'm gonna when you try to model this system, then you got to have an input, then you got to have an output. So you look at this current description, right, and then you decide, okay, what's my input? My input must be the dollars, right? How much dollar you put in, then there's a certain amount of drinks, number of drinks is produced. So let the input be X and equal to certain amount of dollars. And then I'll let the output Y to be the number of drinks. Okay. So already by observing it, you see that, okay, if I represent the system using an operator M, and you look at the relationship between the dollars you put in and the number of drinks you're getting, right? The Y equal to how much of X? 1/2. Okay? So you put in how much of dollar, you get this many of drinks. So essentially, this is your system. Okay? You get a simple math description of the current real life problem. So now let's see, is this a linear system or not? That's the next step. So first, I'm going to use a little more a cumbersome way to check. Basically means instead of I check the superposition, I'm going to check both the additive and homogeneous properties separately. All right. So let's check additive property first. So back to the description of the additive property. What do I need to show, right? I need to show essentially, well, before we move ahead, I'm going to let x1, not t anymore, so let x1 and x2 as 2 inputs. Okay, so basically 2 different dollar inputs. So what I need to check is, so I need to check this mx1 plus x2. Is it the same as, so for now I had to put a question mark, right? So I don't know if they're the same or not. Or is it the same as mx1 and then plus mx2? That's what I need to do. So the other thing I also want to caution everybody at this stage is, for math, when you write your solution, I highly encourage you to write it precisely, because I've seen a lot of people cutting corners. You see I have a question mark here, right? But a lot of people, when they write, they delete the question mark, they just write this equal to this, but they're not precise, right? Because at this stage, you don't know whether they are the same or not. That's why I put a question mark here, okay? So bottom line is, we're going to write an answer for the left, and we're going to write an answer for the right, and then we compare the answers, and we make a decision whether equal sign holds or not. Okay. So that's what I require you to do at this stage. Do not write equal sign right away, right? At least you write the expressions, the left and right expressions separately. Find the answers for them separately before you see the left equal to the right or left not equal to the right. Okay. So let's take a look at in this case, what is the system output when the input is x1 plus x2. Okay. Again, the simple question, whatever inside the bracket is the input. And the current system already have modeled as 1/2 x. So when your input x, you see this x here, right? What do? You're replacing this x with what? x1 plus x2. Okay. So you get 1/2. You replace the x with x1 plus x2. So you see very much like this, right? If I give you f of x squared, and you say, okay, what is the value of f of 3? You do what? You replace the x with 3, and you get 9, right? Yeah. So of course, right now we're replacing things not with numbers, but with symbols. Okay. It's the same thing, though, right? So that's what we get for this input. This is the output. So now let me check the other side. What is mx1 plus mx2? So mx1, you go back to your system. You replace the x with x1, and you get 1/2 x1. Go back to your system, replace x with x2. You get 1/2 x2. So now things are pretty clear, right? So when you compare these two expressions, they are the same. That means additive property is satisfied. So now you can conclude additive property is satisfied. Excellent. So this simple example, I want you to just quickly look at this sample here to establish a very simple reflection is you look at the bracket, then you know what the input is. Then once you know the input, then you look at the original system, then you know what you should do with the variable x. So you're replacing the x with the new inputs. Now you might have a more complicated than x1 plus x2, it doesn't matter. Just replace that x with whatever inside the bracket. Okay, good. So now let's look at the second property, that homogeneous property. Homogeneous property means you need to check, are these two expressions the same as each other or not? Okay, you need to check this. Again, I have a question mark at it here because I don't know yet, right? So you're not supposed to put down this equal expression right away. So again, I have to produce a result for the left and the right separately. So let's look at the expression for the left side first. Follow exactly the same way of doing it, thinking. What is the input now? C times x of t. What is the system? 1/2 x. So what should I replace the x with? C times x of t. Excellent, right? So you get 1/2 c times x of t. That's it. You can't do anything more simpler than that now. Just leave it. And then the other side is c times m x of t. It's just c times 1/2 x of t. Right? Sorry, why do I use x of t? I don't have a t here, right? Just forget about t here. I don't have a t here. Just x. Okay. So obviously they are the same, so that's why you can see the homogeneous property is satisfied. Both properties satisfied. You got a linear system. Oh, cool, right? So that the Starbucks system is a linear in this case. You might actually also probably already concluded, because when you look at y equal to 1/2 x, it's a straight line, right? It's a linear line. However, you have to be careful, though, right? The next example will show you a little bit different perception, all right? So let me change this question slightly, all right? Let's change this question slightly. So Starbucks is giving out promotions. You buy 3, get 1. So if it has a 3 buy 3, get 1 system, so how does that work? So basically, you put $2, you get 1. You put $4, you get 2. And you put $6, according to buy 3, you get 1. You get 3 plus 1. So that's buy 3, get 1 example, right? Okay. So what would be the system linearity for the Starbucks coffee when it's on promotion? How do we check that, right? Okay. So I'm going to use a very similar approach, okay, but unfortunately, we cannot actually arrive at a single mass expression for the current, rewarding system. Right? It's not like the previous one, y equal to 1/2 x. But I can still use the similar concept, okay, to prove the system linear or nonlinear. So the similar concept basically is very similar, right? You put $1 into the system, and you get a number of drinks. Good? Okay. So I'm going to use this to demonstrate. If I put $6 into the system, okay, if I put $6 into the system, how many drinks should I get? I mean, $6, right? I get 4 drinks in this case. But what is $6? $6 is basically the $2 plus the $4, right? Okay. So I'm not changing anything. Right? That's based on the system. So then, what is the $2 plus the $4? How much drink do you produce when you buy separately? When you spend $2, you get 1. When you spend $4, you get a 2. So you get 3 drinks. So now you can clearly see m of a 6 is not the same as m of a 2 plus m of a 6, m of 4. That essentially, what does it tell you? Which property is not satisfied? Additive property is not satisfied. So now you can see additive is not satisfied. Hence, the system is nonlinear. Okay? That's a very simple demonstration. You don't even have to have an expression for the system. Okay? So I'm going to stop here, but before I stop, I want you to give it a little bit of thoughts here is that for the Starbucks system, which is 1/2 x in the previous example, now I'm going to change the Starbucks system into 1/2 x plus 1. Would you think the system, or you can check, is still linear or become a nonlinear? All right? Yeah. Okay. We'll see you on Monday, next week. Yeah.
If we have proof, one of them is not